Welcome to This Explainer. Today, we're going to uncover exactly why the octopus is, hands down, one of the most absolutely fascinating creatures in the entire ocean. You know, when we think about life beneath the waves, it's pretty easy to just assume that biology works roughly the same way down there as it does for us up here on land. But, well, the octopus throws literally all of those assumptions right out the window. We're going to look closely at their unique physiology today, specifically zooming in on the incredible internal engines that keep them alive.
Okay, so let's dive right into this by asking a fundamental question about their bizarre, almost alien-like anatomy. How many hearts does it actually take to survive the deep ocean? For humans, and honestly for most mammals, the answer is a simple, highly efficient one. We just rely on a single heart to do all the heavy lifting, pumping oxygenated blood to every extremity of our bodies. But the ocean? It's a vastly different environment, and it demands entirely different evolutionary solutions.
That's right, the answer is 3. An octopus doesn't just have one backup heart, it has an entire cardiovascular system built around 3 distinct pumping stations. And this massive number completely changes how we understand their survival. I mean, it sounds like something straight out of science fiction, right? But it's a very real, very vital adaptation. Having 3 hearts isn't just some anatomical quirk, it's a highly specialized biological design that lets them function in a really demanding underwater habitat. In fact, it's such an intense system that there's a fascinating trade-off here. The main heart, the one responsible for circulating blood to the body, actually stops beating when the octopus swims. Crazy, right? Because swimming is so exhausting and temporarily shuts down that central engine, you'll much more often see an octopus just choosing to crawl along the seafloor to avoid exhaustion and conserve its vital energy.
Step 1. 2 hearts pump blood to the gills to absorb oxygen. Step 2. The third heart circulates oxygen-rich blood to the body. So these 3 hearts don't just all do the exact same job. There's a strict, highly specialized workflow happening here, functioning almost like a biological relay race. First off, 2 of these hearts are entirely dedicated to the gills. Their sole purpose is to act as the starting runners, pumping blood directly to the gills where oxygen from the surrounding water is rapidly absorbed. Then the baton is passed. Once that blood is freshly loaded up with oxygen, the third heart takes over. This primary systemic heart is responsible for taking that newly oxygen-rich blood and forcefully circulating it throughout the rest of the octopus's body. It is just an incredible segregated system of biological engineering.
But it's not just the number of hearts that makes the octopus so unique. It's the actual fluid pumping through them. Iron-based hemoglobin for humans versus copper-based hemocyanin for octopuses. Think about our human standard for a second. That iron is what binds to oxygen in our bodies, and it's exactly what gives our blood its signature red color. Now, contrast that with the octopus, which uses something entirely different, a copper-based protein called hemocyanin. Because they use copper instead of iron, an octopus's blood is literally blue. It's a wildly different approach to the exact same biological necessity.
Hemocyanin, a copper-based protein that gives octopus blood its blue color, replacing the iron-based hemoglobin found in humans. So the absolute crucial point here is this specific protein, hemocyanin, because it completely transforms their internal chemistry. It's not just some neat party trick that changes their blood color for fun. It's a fundamental replacement of the iron-based hemoglobin system. Hemocyanin relies on copper to bind and carry oxygen atoms through the octopus's vascular system. By shifting from an iron-based biology to a copper-based one, the octopus unlocks a completely different method of surviving the immense pressures and harsh realities of marine life.
Cold, low-oxygen waters. This brilliantly illustrates the evolutionary payoff, because these bizarre traits aren't just random flukes. They are absolute necessities for surviving their specific, extreme environment. You see, a lot of octopuses live in waters that are exceptionally cold and notoriously low in oxygen. To put that into perspective, if humans somehow went down there, our iron-based hemoglobin would essentially be completely useless. It just doesn't perform well enough under those specific environmental stresses to properly bind oxygen in freezing temperatures. But that copper-based hemocyanin? It absolutely thrives there. It helps the octopus transport what little oxygen is available with incredible efficiency in those freezing, oxygen-depleted ocean depths.
Copper-based hemocyanin replaces iron. It transports oxygen highly efficiently, and it's perfectly adapted for extreme ocean conditions. When you put all of these pieces together, you're really looking at a masterclass in survival. These physical traits perfectly combine to allow the octopus to thrive where other creatures would quickly fail. First, they've completely swapped iron for copper-based hemocyanin. Second, this swap guarantees that oxygen is transported highly efficiently.
And finally, the whole shebang makes them perfectly adapted for extreme ocean conditions. The 3 hearts pumping this specialized blue blood isn't an accident. It's a finely tuned survival mechanism, meticulously crafted by evolution to conquer the cold, low-oxygen waters of the deep.
If copper-based blue blood is the ultimate hack for low-oxygen oceans, just how efficiently are these fascinating creatures built? I want to leave you with this final thought to ponder about the brilliant, strange adaptations of the natural world. If copper-based blue blood, driven by a 3-heart system, is the ultimate biological hack for surviving in low-oxygen oceans, it really makes you wonder about the sheer mechanical efficiency of these creatures. We've seen how they have completely rewritten the rules of circulation and oxygen transport. It challenges us to look differently at what it really means to be perfectly adapted to our environment. Thanks for joining me for this explainer, and keep questioning the incredible world around us.